promised already, we have to cover some portions at least from the so-called Fourier series representations. So this thing, sorry? 3. Maybe 2. Maybe 2. Because 3 consecutive hours will be too much for me as well. So I may become tired, then we will stop. It may be 2 hours. We'll see. This thing, the Fourier series, is critical because of several things. It's a completely new representation of a signal, but it is a bit specific to periodic signals. So the Fourier series representation will not be available for us, for non-periodic or normal signals, like starting at some point and ending at some other point. These will be only for periodic signals. And we will start with the continuous time representation. Now, in the continuous time representation, the representation itself was very important for us to determine the linear time invariant system response to the signal. So we were saying, let's start with a discrete time signal. We were saying that it's consisting of impulses, right? We made a representation of x of n from several impulses, like x minus 1, x n plus, delta n plus 1, plus x0 delta n plus x1 delta n minus 1, x2 delta n minus 2, from the top to the bottom. It's a summation of all these things, and this x minus 1 is x of minus 1. Delta n plus 1 is an impulse at n is equal to minus 1. So we were isolating every item of our signal to individual impulses. And why were we doing that? And the summation of these things was, what was that? It was summation for k, x of k, delta n minus k. Right? That was the representation of x of n. And to each individual impulse, since we know the impulse response of the system, we said that the response is x minus 1, h n plus 1. Because to delta n plus 1, the response is h n plus 1, where h n is the impulse response. So we were shifting the impulse responses and scaling with the same scale as x minus 1. This is x0 h n. To this, it's x1 h n minus 1, etc. And the summation is therefore the response to this final summation, which is summation for all k, x of k, h of n minus k is equal to y of n. The response. If x is the input, y is the output. This is how things work. Now notice one thing. We are trying to represent our signal. That's the critical thing. This time representation is a representation in terms of impulses. In continuous time, things are a little bit different, but similar still. It was like this. X of t is equal to the integral x tau delta t minus tau d tau. Instead of that summation with the discrete impulses here, now we have an integration of shifted and scaled impulses, but still it's a representation. Now we will come up with a completely different representation of the same signal in continuous time. We will start with the continuous time only. And we will say that let's try to represent our signal as a summation of impulses. Let's give an example to that. summation, sorry, not impulses, but a different kernel signal. It's a basis signal in some sort. We are like representing a vector using basis vectors. Here, the basis vectors are impulses. Here again, the basis vectors are impulses, but this time, the basis will be rotated, sort of, another basis, on the space of signals. It's not a space of vectors anymore. This is a space of signals, and we are trying to represent a signal using combinations of other basis signals. And those basis signals are, these are the linear coefficients, AKs, times e to the minus j omega 0 k. Okay. We can times t. Sorry, we need to put something like this. This omega 0 times k will correspond to a specific entity which is called the frequency. And this frequency, on the other hand, as you can see, is not continuous on the frequency axis. So that is the frequency which is called omega, but that omega is not continuously varying. Like, not every omega is a possible frequency for this summation. Every omega that is possible in this representation must be an integer multiple of omega 0, which is also known as the fundamental frequency. So there is a fundamental frequency, omega 0, that you have to determine. And there is a component of that frequency. So it is something like this. Let's think of a square waveform like this. It's going to the left and to the right. A pulse waveform, and it is certainly periodic, right? You can see that. What is the period? The period is from here to here, and let's call it capital T. This period is the fundamental period, and notice that multiples of that will also correspond to periods, like 2 times capital T will be also another period, but this is the fundamental period. And this fundamental period determines the fundamental frequency that we are talking about. So what is omega 0? Omega 0 is equal to 2 pi over capital T, or 2 pi times 1 over t. 1 over t was the fundamental frequency in hertz, 1 over seconds. 2 pi, by multiplying with a 2 pi, it becomes radians per second. Everything will be 2 pi normalized then. But this is the fundamental frequency. And at this fundamental frequency, this expression is indicating us that for such a periodic signal, it consists of summations of several sinusoids. Remember that in e to the j omega t, or e to the minus j omega t, it doesn't really matter, it's just a flipping around in the omega axis, is a sinusoid. It's a sine wave or a cosine wave, in fact a combination of both. So it's a sinusoid with frequency omega, and that omega is starting by k is equal to 0. Let's consider k is equal to 0 case. What does that mean? What kind of a component does it correspond to? When k is equal to 0, omega 0 times k is 0, e to the 0 is 1. So there is a component called A0 here. Plus. What is the next component that we have? A1 times e to the minus j omega 0 t. This e to the minus j omega 0 t is a sinusoid with frequency omega 0. So it looks like, for this particular case, it looks like a sinusoid like this. This is the sinusoid. And I guess it doesn't have to be like that for any kind of a signal, but I guess that the peak value of the sinusoid should be somehow related to the peak of this sine. So A1 will be determined like this. If this is a plus and minus symmetric rectangular pulse like this, could you guess what A0 is for this particular example? If this is our x, what can you say about A0? No. A0 is, as you see, a number. And there is no sinusoid associated with that. Because that sinusoid has 0 frequency. So that's the DC value. It's the average DC value. This is the DC component. All right? The next one is the first harmonic. That's the name. This is the first harmonic. And then comes another term with twice the frequency of this one. It cannot be 1.3 times the frequency of omega 0. So what is the twice frequency case? It must be something like this, for example, right? So this sinusoid has twice the frequency. I don't know the magnitude. I have no idea about that. But somehow that's a magnitude. It can even be 0, by the way. All right? So that magnitude, whatever it is, it's here. A1 is that magnitude. And then plus A2 e to the minus j 2 omega 0 t, and then plus A3 e to the minus j 3 omega 0 t, plus etc. It goes on like that. And as a matter of fact, we even have negative indices like a minus 1 e to the j omega 0 t, a minus 2 e to the j 2 omega 0 t, etc. To the left hand side, the summation also goes on. This is a completely new representation of our signal. And notice that it is somehow similar to this representation. We are combining some scales, x minus 1, x0, x1, x2, etc. And we are multiplying these scales by some root or kernel signals and combining them to get our signal. Here the situation is the same. We are getting an x of t by combining scaled versions of sinusoids at different frequencies. But why do we do that? What's the matter with us? We already have that representation. So why are we just struggling to get just another representation? There are so many reasons to do that. One of them is that it gives us a completely new axis for the representation of our signal. Previously, the axis was the time axis, and the impulses were located in time. But this time, the axis is not related with time anymore. The axis is related with frequency. This scale, A1, is showing a particular power of our signal, a component, power component of our signal, with this particular, associated with this particular frequency omega 0. So how much power does this signal have at omega 0, for example? That power is related with A1. How much power does it have at 2 omega 0? That is A2. So we are now drawing our signal not on the time axis, but on the so-called frequency axis. like this. This is A0. This is A1 at omega 0. A2 at 2 omega 0. A3 at 3 omega 0, etc. It goes on like this. It may finish at some point, by the way. Let's assume so. Let's say that all the other A coefficients become 0 after some frequency. By just looking at that frequency value, this is 3 omega 0, so 4 omega 0, 5 omega 0, and 6 omega 0 is the last, let's assume. It's just an assumption. And after that, we have nothing, let's say. Then we can see a very nice layout of the signal, of this periodic signal, with respect to its harmonics and the frequencies of those harmonics. For example, we say that the signal, by the way, if you're talking about power, of course, you have to take the magnitude squares of these values, A0, A1, etc. But nevertheless, if the value of A is large, then it means there is a high power component at that frequency. And if it is low, like this is small, let's say, then there is not much frequency content at that frequency for this signal. And it may mean something. We may analyze it. We may say that this signal is having a large low frequency. The frequencies closer to 0 are lower frequencies. Low frequency content of this signal is large. The mid-range is low, and the higher frequency contents around here are again somehow large, let's say. So what does that mean? It may mean that the harmonic or the frequency content corresponds to a specific musical instrument. We may recognize our instrument by just looking at the frequency content, which is known as the spectrum. We look at the spectrum and say that it's a violin. We may look at the spectrum of another instrument, and we may say that it's a saxophone, for example, another instrument, which has different frequency characteristics. Some of them are larger at some other frequencies, lower at some other frequencies. Or we may say that this is our recording, and in our recording this is too low for an instrument, let's say. So we want to increase it, boost it. Or let's do it like this. The higher frequency content is too low. We want to exaggerate, make it larger. How can we do that? That is called filtering. In the previous years they were more popular, but we used to have equalizers in hi-fi systems. Do you remember them?
Yes.
Yeah, you know them, right? Those equalizers, and there were voltmeters as well. The music was showing the frequency content. So the right-hand side corresponds to high frequency and the left-hand side corresponds to low frequency. That voltmeter thing internally is taking the Fourier transform of your signal within a time duration and displaying the energies of the frequency contents. So if this is not enough for you, you just have to boost them, you have to increase them. That's a design issue that we will see. We have to design our filter which increases the higher frequencies and decreases the lower frequencies. That's the equalizer setting that you do in musical instruments. So we are now able to see on the axis of frequency, which is a very good thing. It means a lot of, it has a lot of insight, because human ear is also distinguishing sounds with respect to the frequency content. Higher frequencies are high pitch waveforms, lower frequencies are bass things. So that's how we hear. But there is one other important reason. about why we need this kind of a representation. It's not only the axis, but it's due to a very nice property of linear and time invariant filters. It is as good as this one. Remember that a linear and time invariant filter is producing every delta, when a delta is input, the output becomes H. This relation or such a relation also exists if our representation is in terms of sinusoids, complex exponentials, e to the j omega stuff. And let's see what I mean. We will start with only one expression. Do we have that expression here? Well, anyway, let's assume that that's an example, and this example requires convolution, by the way. In this example, we have an x of t consisting of only one sinusoid, e to the j omega t. This sinusoid has frequency omega. It's not a variable, okay? It's a particular omega. Let's call it omega 1, okay? A certain frequency. By the way, it is clearly fitting to our representation here, x of t, summation for all k, ak e to the j omega 0 times k times t. But there is only one ak, which is a minus 1 or a1, whatever. It only has one harmonic. If this is our input, and if it goes into a linear and time invariant system, a LTI system with impulse response HD, what is the output? For that, you need to convolve. You need to make a convolution. We have to convolve. The output is y of t, of course. Y of t is x of t convolution h of t, which is from minus infinity to infinity. I will use h of t convolution x of t. I'll try to interchange because I want to leave h of tau as it is. Normally I would write x of tau h of t minus tau, right? Do you remember that? That's the convolution. X of tau h of t minus tau d tau. I'm writing it as h of tau x of t minus tau d tau. It's the same. What is x of t minus tau? It is e to the j omega 1 t minus tau. This is x of t minus tau d tau. And e to the j omega 1 t goes out of the integral, and e to the minus j omega 1 tau will be remaining inside the integral. Let me write it. Do you agree with this? Okay. Now, this thing is something to be evaluated, and we cannot evaluate because we don't have a particular representation of h. We don't know what h is. It is just h. But whatever it is, let's call it a capital H. Is it a function of time? It's not a function of time. There is no time index left inside this integral. All the tau values are integrated out, but it is a function of, or it varies, changes with changing omega 1. This thing is indeed a function of omega 1. It depends on the value of omega 1. If you change omega 1, this integral will be different. If you change it again, it will be again different, with a different numerical value. It's a complex valued function of omega. And how about this? Well, it is the same as the input. So I'm going to write it. E to the j omega 1 t h of omega 1. Now this input-output representation is very, very nice, because it is telling me that if a complex exponential like this goes into our system, then the same complex exponential goes out, scaled only. This is a complex value. Okay? It's a value. That depends on omega 1, but for a certain omega 1, it is just a numerical value. So that's a scale. So a signal goes into our system, and the same signal goes out, only scaled by a complex value. That sort of property is only valid for sinusoids. If you input a sinusoid into an LTI system, the same sinusoid goes out, scaled. And there is a name to that. It's an interesting name that is used from linear algebra. Do you remember such a formulation? For a matrix A, it's a square matrix A, there exists a vector x, which when you apply it to this matrix, that is, when you multiply this column vector with the square matrix, suppose that the sizes fit, is equal to the same vector output, only scaled. Do you remember this equation? You might have heard about that. It's the eigenvalue, eigenvector decomposition. That was the name. If you don't remember it, just search through your linear algebra and you will encounter this. Such a vector, x, is called the eigenvector of A. And here, A is your system, x is your eigenvector. This thing somehow resembles that, and you must see the similarity here. An x vector is applied to a system, and the same x goes out only scaled. And therefore, we call this signal to be the eigensignal of LTI systems H. That's the name, an eigensignal. And eigensignals are very good. They don't change. This doesn't happen to any other kind of a signal. For example, when an impulse comes in, it's not an impulse that goes out in general. I'm talking about general source of all sorts of LTI systems. What goes out? If an impulse comes in, impulse response goes out, and they are different. It's not an impulse. But if a sinusoid comes in, a sinusoid goes out. Then that's an outstanding property of sinusoids. That's why we want our x of t to consist of several sinusoids, not necessarily only a single one. What would happen, I'm erasing the bottom part now. What would happen if it's not only one sinusoid, but two sinusoids? Suppose x of t is not, let's proceed one step further. If x of t is this, then the output is that. How about if x of t is a1 times e to the j omega 1t, then what is the output? A1 times, because it's a linear system, right? Let me multiply it here. Now, plus a2 times e to the j omega 2t. Suppose our signal is not this, but this plus this. Then what's the output? The output is this plus e to the j omega 2t times a2 times h of omega 2 this time, a different scale. The first one is scaled like that, the second one is scaled like that, and they are added. What happens if this summation goes on? The same summation goes on output. That's how we determine the system response for combinations of sinusoids. And that's why, as a summation, we have for all k, ak e to the j omega k, I will say, t. And I want to represent it like this. X of t, our input. And it goes into my system. And the output is y of t, which is the same summation. Every ak will produce the same ak. Every e to the j omega kt will produce the same e to the j omega k t. But each of these things will be scaled by h of omega k, one by one, for every k. So this input-output relation is, as you see, as easy as the input-output relation for the impulse response in time domain. And this is quite specific to frequency representation, or quite specific to the complex exponentials. Let's see some examples of these things. Now, of course, please notice that we didn't see the method about how to determine AK for a given signal. If I give you any x of t which is periodic, I give it to you, can you find the AKs? Of course you can, but we didn't see how to do that yet. That is requires a methodology. And for every periodic signal, there is a way to determine AK. For example, x of t is, let's say, cosine 4t plus cosine 7t. This is our signal. It is given in terms of sinusoids, and this is the easiest class of signals where you can determine AKs. And how do you do that? By just representing cosines or sines in terms of the corresponding complex exponentials. You have to just split these things into complex exponentials. And you have to know that. You have to know the complex exponential formalism for that. Do you remember them? What's the cosine in terms of complex exponential? What is cosine theta? It is this. These Euler's expansions, the formulas for such trigonometric expansions, I guess they will be available to you in the examination. So you will know these things. And of course, what is e to the j theta in terms of cosines and sines is another issue. It's equal to cosine theta plus j sine theta. So there is an inversion formula for that as well. And you have to know them. Or at least you have to try to learn and use them. So for a cosine for t, we have 1 over 2 e to the j for t plus 1 over 2 e to the minus j for t plus 1 over 2 e to the j 7t and 1 over 2 e to the minus j 7t. So now it's quite clear that the Fourier series coefficients are, whatever index you may use, they are all 1 over 2s. But we do have a problem here. Remember that any frequency that you have here, which is omega k, must be equal to a fundamental frequency times k. So you are running into a difficulty here. What is the fundamental frequency of this thing? There is such a fundamental frequency that all the other harmonics, all the other frequencies are integer multiples of that fundamental frequency. What is that fundamental frequency? 4 is an integer multiple of that fundamental frequency, and 7 is also an integer multiple of that fundamental frequency. What is that fundamental frequency? I'm asking for a number here. 1. That's true. Because 4 is an integer multiple of 1, and 7 is also an integer multiple of 2. And there is no larger number frequency which have this which have these frequencies 4 and 7 as the integer multiple of that common fundamental frequency. So here, in fact, omega 0, as you have suggested, is equal to 1. Then, if omega 0 is 1, what do we have? It's equal to 1 over 2 times e to the j times 1 times 4 times t plus, we will continue, this 1 over 2, what is the corresponding k now here? The corresponding k is 4, which means this is equal to a4. It's not a1. a4 is this, plus 1 over 2 e to the j times 1 times minus 4 times t. So what is this 1 over 2? It is minus 4. So the index k is minus 4 here, and this 1 over 2 is actually corresponding to a minus 4. One over 2 e to the j 1 7t. So this 1 over 2 is a 7 plus 1 over 2 e to the j times 1 times minus 7 times t. So this 1 over 2 is a minus 7. So you have to be careful about drawing these Fourier series coefficients and labeling them accurately. Usually students fall into this trap. They say that a1 is 1 over 2. Sometimes they are clever enough to say that this is a minus 1, because that's the negative frequency of that. And this is a2 and a minus 2. That's a wrong answer. Okay, you shouldn't say that. This is a4, this is a minus 4, that's a7 and a minus 7. And if I want you to plot this on the frequency axis, omega, you have to plot it like this. This is zero frequency. This is omega 0, which is 1, omega 2, omega 3, omega 4 is 1 over 2, and 1 over 2 again at minus 4. So this is 0, 1, 2, 3, minus 1, minus 2, minus 3, and this is minus 4. That's how you plot AKs on the axis of frequency. A4 and A minus 4 are 1 over 2, 5, 6, 7 is also 1 over 2, and minus 5, minus 6, minus 7 is also 1 over 2. The others are zeros. So it has basically these 4 harmonics at 2 distinct frequencies. Usually these 2 are symmetric, as you see. They become completely symmetric if it's a cosine. They become conjugate symmetric in general. When the values of AKs are complex, they may become complex as well. We will see an example of complex valued Fourier series coefficients as well. So this is the answer that I expect when I give you just this. This is x of t. It's a periodic signal, and therefore Fourier series coefficients of that exists. What are the Fourier series coefficients? That means what are AKs? And you have to give me this plot, or say it in a sentence like this: A4 is this, A minus 4 is this, A7 is this, and A minus 7 is that, and all other AKs are zeros. That is the answer that you have to give. If you write it like this, and the question is, let's say 10 points, if you write it like this, you will get like 4 points. Of course, these correspond to the Fourier series coefficients, that's for sure, but which index Fourier series coefficient does it correspond to? That is more critical. In order to get 6 more points from that question, you have to say that this is A4, A minus 4, A7, and A minus 7. Give me this answer. Then you will get 10 points, because you clearly found the Fourier series coefficients. Let's see another example. Then we will give a break, and then we will continue with the systems. A cosine is too easy, as you see, for determining the Fourier series coefficients, because these values are all reals, 1 over 2 everywhere. How about sinusoids? Do you remember them? For example, if the same question was asked like this: x of t is equal to sine 5t plus 3 sine 6t. Okay, I'll do it in another way. Sine 3t plus 3 sine 6t. This question. Let's find the Fourier series coefficients now. That is equal to, the Euler's expansion for this one is a little bit more complicated. It is 1 over 2j, right? This is the complex j. E to the j3t minus e to the minus j3t. So what is the difference between the cosine version and the sine version? In the sine version, this becomes 1 over 2j instead of 1 over 2. And instead of a plus sign in between, this becomes a negative sign. So that is the difference. Plus, there's a 3, so 3 over 2j I will write. E to the j6t minus e to the minus j6t. Now, first things first, what is the fundamental frequency again? What is the largest common frequency where 3 is an integer multiple of that and 6 is also an integer multiple of that? What is that frequency? 3, right. So this time things are a little bit different. Omega 0 is equal to 3. You could say that the fundamental frequency could be considered as 1, but it wouldn't change the frequency value when you plot it. Okay, it would correspond to the same plot here. So if omega 0 is equal to 3, then this 1 over 2j corresponds to what? A index what? What's the index? Is it A1, A2, A3, A minus 1 what? It is multiplying e to the j3t. So 3 is 3 times 1. So that thing is A1. So A1 is equal to 1 over 2j. A minus 1, here as you see, the index is 3 times minus 1. So the index here would correspond to A minus 1, and that is minus 1 over 2j. How about this 3 over 2j? 3 times 2, so index is 2 over there. A2 is equal to 3 over 2j, and A minus 2, because this is 3 times minus 2, minus 6 it makes, is equal to minus 3 over 2j. Now can we draw this? Can we plot it? Unfortunately not, because j is in the denominator, it appears somewhere, so it's not a real value. We cannot plot it on a real valued axis, but we may plot it like this then. Since everything is just multiples of j, this is still quite simple. For other things, it's impossible to draw a function with a complex value. You can draw it in several ways. You can draw the real part and the imaginary part, or the magnitude and the angle. Every complex number has these two properties, the real part and the imaginary part, and the magnitude and the angle. So let's draw, for example, not AK, but AK times j. Then it becomes real, right? All of these will become real. This will be 1 over 2, this will be minus 1 over 2. J's will be cancelled. This is omega frequency. What is the fundamental frequency? It is 3. So here it is 3, and we have 1 over 2. For A1. And at minus 3, we have A minus 1, and the value of that is minus 1 over 2. When you multiply every part by j, j's will cancel and you will have minus 1 over 2. At minus 3, the frequency at minus 3, we have this. And at twice the frequency, which corresponds to the frequency of 6, we have 3 over 2, which is 3 times larger than that. And at minus 6, it is this, minus 3 over 2 as the value. So this is the plot that we may expect. Okay? Unfortunately, these examples are still too primitive. It contains only only a few cosines and sines. You may combine a cosine with a sine with a cosine. These values may be different, the frequencies may be different, but things will not change. A good exercise for you to become fit and ready for the examination could be to put some phase here. For example, sine 3t minus pi. Pi is too trivial, sorry. 1.2, let's say, plus 2.5 cosine 6t plus 0.7. Right? Then what? Yeah, it doesn't change. It doesn't change much, but you have to be quite careful about this phase, because this time it will be in the exponent will have some constant terms plus 0.7j sort of thing. That e to the 0.7j will be a number. It is like the number that you have here. There will be another coefficient appearing here. So that will contribute to the Fourier series coefficient values. So these 1.2 and 0.7 in the exponents, complex exponents, will be appearing in the Fourier series coefficient terms. So the Fourier series coefficient terms will not be 1 over 2 and 2.5 over 2 only. There will be complex exponents of these numerical phase values as well. They will come in. Do you feel that you can manage such questions? I mean, you have to make sure that you can also find the Fourier series coefficients of these things. This time the Fourier series coefficients will be not purely imaginary, not purely real, they will be complex, containing some real part and some imaginary parts. They will be a little bit difficult. I want you to make sure that you can solve this question. If any of you is not able to solve that question, please come to me. Okay, we have to work it out in my office. Find me and ask, or find any assistant, all right, and ask them. Don't come to the exam without solving this particular example, at least. You have to find the Fourier series coefficients of those things. You have to be able to expand it in the Euler form. Now we will give a break of 15 minutes. After the 15 minutes break, we will continue with, now this time, passing these signals through LTI systems. What's happening? Is the formulation okay or not? We will see that. So let's give a break now.